Respected sir and other viewers, Assalamu alaikum. My name is Sadia Iqbal and I am from BT department. Today my presentation topic is MOR material. It is basically metal organic framework. First of all, I will introduce about metal organic framework. Metal organic framework are inorganic organic hybrid materials that represent an advanced class of solid crystalline materials. Inorganic building units like metal ions, cluster of metal oxygen clusters are interlinked with the help of organic linkers. Now I will define about metal organic framework. The term metal organic framework or MOF has come to define compounds where metal ions or clusters are bridged by coordinating organic linkers to form extended structures in up to 3 dimensions. Now what are microporous materials? Microporous materials can be defined as solids containing interconnected pores of less than 2 nanometer in size. Thus they possess large surface area, typically 300 to 2000 milligram, as measured by gas absorption. Examples include the zeolites, metal organic frameworks, clays, carbon, etc. Now what are mesoporous materials? Mesoporous materials are typical type of nanomaterials with ordered array of uniform nanochannels. These materials have important application in a wide variety of fields such as separations, catalysis, absorption and advanced nanomaterials. Now here are some examples of micropores. A microporous material is a material containing pores with diameter less than 2 nanometer. Examples of microporous materials include zeolites and metal organic frameworks. Porous materials are classified into several kinds by their size. Here are some properties of microporous and mesoporous materials with MOR materials. First one is high surface area. The surface area of typical MOR material ranges from 1000 to 10,000 milligram, which can exceed those of traditional porous materials such as zeolites and carbons. The pores of MOR materials are highly ordered due to their crystalline structure. Next one is catalytic activity. In catalytic activity, metal sites in a MOR material can include those within the inorganic building sites of the framework, dark blue. Those that are insured to the organic linker molecule as metal complexes, pink, purple, and those which reside within the pores, light blue. Next one is tunable pore size. In tunable pore size, due to the ease of the formation of interpenetrated and fragile structures, the largest pore aperture reported in the metal organic framework is 8.5 nanometer and the value for equivalent organic frameworks is only 5.8 nanometer. Next one is selective absorption. CuPTC, a kind of metal organic framework, was used as an absorbent to selectively absorb methylene blue from dye-mixed wastewater. The synthesized CuPTC was characterized by scanning, electron microscopy, transmission, electron microscopy, Fourier transform, infrared spectroscopy, X-ray diffraction, and X-ray photoelectron spectroscopy. The results indicated that the synthesized CuPTC have an octahedral structure. Here we can see microporous and mesoporous metal organic frameworks. Now I will discuss about the role of MOR materials in water pollution and air pollution. First of all, I will discuss about water pollution. First one is metal organic removal, heavy metal removal. Metal organic framework materials can selectively absorb heavy metals like lead, mercury, cadmium, and arsenic from contaminated water sources. Next one is organic pollutant removal. Metal organic framework materials can effectively absorb organic pollutants such as pesticides, pharmaceuticals, and industrial chemicals. Next one is water purification and desalination. Because of MOR materials has various pore geometries, high surface area, easy functionalization, and adjustable porosity. These unique properties make it irreplaceable in the absorption and removal of various toxic components in wastewater. MOR materials can be used in advanced water treatment processes including filtration, ion exchange, and desalination. Now I will discuss about air pollution, role of MOR material in air pollution. Air pollution is the contamination of the air due to the presence of substances in the atmosphere that are harmful to the health of humans and other living beings or cause damage to the climate or to materials. Next one is VOC capture. It is basically volatile organic compound. Volatile organic compound are a large group of chemicals that are found in many products we use to build and maintain our homes. Once these chemicals are in our home, they are released out of gases into the indoor air we breathe. Next one is nitrogen oxide removal. In nitrogen oxide removal, MOR materials can act as catalyst for the reduction of nitrogen oxide emitted from industrial processes and vehicle exhaust. Next one is particulate matter filtration. MOR materials can be integrated into air filtration systems to capture particulate matter, including fine particles and toxic airborne pollutants. And the fourth one is selective gas separation. In selective gas separation, MOR materials can be employed in gas separation processes to remove harmful gases such as carbon dioxide and sulfur dioxide from industrial emissions. Here we can see the diagram greenhouse gases, MOR materials, and chemical warfare agents. Now I will discuss about designing MOR materials. First one is pore size. In tunable pore size, designing MOR materials with tunable pore size to target specific pollutants or gases for absorption or separation. Next one is optimal pore diameter. Consider the size of the target molecules or ions to ensure they can effectively access and interact with the pores of the materials. Next one is surface area. In high surface area, maximize the surface area of MOR materials to enhance absorption capacity and catalytic activity. Next one is porous structure. Incorporate a highly porous structure such as interconnected cages or channels to increase the surface area available for absorption or catalysis. Third one is functionalization. Surface functional groups. Introduce specific functional groups on the surface of MOR materials to enhance selectivity towards target pollutants or gases. Now I will discuss about some cases about the use of MOR materials. First one is water treatment, removal of heavy metal case study. Researchers from the University of California, Berkeley developed a metal organic framework called MOF74 for the removal of heavy metals lead ions from the water sources. The MOF74 materials exhibited high selectivity for lead ions and achieved removal from contaminated water. Next one is gas separation, carbon dioxide capture gas study. In this case, scientists at Monash University in Australia designed a metal organic framework known as Note 202 for carbon dioxide capture. Note 20T demonstrated exceptional carbon dioxide uptake capacity due to its large surface area and low pore size. Next case is catalysis, conversion of biomass into fuel case study. Researchers at the University of Michigan developed a metal organic framework catalyst called NU1000 for the conversion of biomass into fuels. Now I will define some challenges and future directions. First one is stability and durability. MOR materials should exhibit long-term stability and durability under diverse environmental conditions. Research efforts should focus on enhancing their thermal, chemical, and mechanical stability to ensure reliable performance over extended periods. Here we can see the diagram MOR materials for chemiresistors for membranes. Next one is scalability and cost effectiveness. Developing scalable synthesis methods and utilizing cost effective precursors are crucial for the widespread absorption of MOR materials. Future researches should focus on optimizing synthesis processes, exploring alternative precursors and developing efficient and economical manufacturing techniques. Next one is regeneration and reusability. Designing MOR materials with the ability to be regenerated and reused for multiple cycles can contribute to their sustainability. Future researchers should explore strategies for easy regenerations, such as optimizing regeneration conditions or developing methods for efficient material recovery. And next one is multifunctionality and hybrid materials. Future researchers should explore the development of multifunctional MOR materials or the integration of MOR materials with other materials to synergistically enhance their environmental performance. Combining MOR materials with other nanomaterials or incorporating additional functionalities can lead to enhanced catalytic activity, improved selectivity, or expanded applications possibilities. Here we can see the diagram chemotherapy, phototherapy, and biotherapy. Now I will discuss about the importance of designing MOR materials. First one is improved performance. Further researches can lead to the discovery and designing of MOR materials with enhanced performance in terms of absorption capacity, selectivity, stability, and recyclability. Next one is cost reduction. Research efforts can focus on developing cost effective synthesis methods and utilizing readily available precursors, enabling the production of MOR materials at a larger scale and reduced cost. Here are some conclusions. Overall, continued researches and development in designing MOR materials for environmental applications is vital for advancing the field, improving performance, and accelerating the absorption of sustainable solutions. It drives innovations, supports policy development, and contributes to a cleaner and more sustainable environment. Thank you. That's all from my side.